Hello everyone, we continue our course of formal language Automata and course, and today will be lecture number 17. This lecture is devoted to method for transforming grammars. We first raise an issue that is somewhat of a nuisance with the grammars and languages in general. The presence of the empty word, the empty string, play a rather regular role in many theorems and proofs, and it is often necessary to give it special attention. I prefer to remove it from the consideration altogether, looking only at languages that do not contain the empty word lambda. In doing so, we do not lose generally, as we see from the following consideration. Let L capital be any content-free language, and let G be a content-free grammar for the language lambda without empty words. And then the grammar we obtain by adding to with a new variable s capital 0, making s capital 0 to start variable, and adding to p capital the production s capital 0 into s capital or empty word, and generates the language L. Therefore, any non-trivial conclusion we can make for the language L capital without empty word will almost certainly transfer to the language L capital. Also, given any context-free grammar G capital, there is a method for obtaining G capital with head so that the language which is generated by the grammar G capital with head is equal G grammar generated by the language generated by grammar G capital without empty word. Secondly, for all practical purposes, there is no difference between content-free languages that include empty word lambda and those that do not. For the rest of this chapter, this lecture, unless otherwise states, we shall restrict our discussion to lambda-free languages. A useful substitution rule. Many rules govern generalization equivalent grammars by means of substitution. Here we give one that is very useful for simplifying grammars in various ways. We shall define the term simplification precisely, but we shall use it nevertheless. What we mean by it is the removal of certain types of undesirable productions. The process does not necessarily result in an actual reduction of the number of rules. Theorem 6.1. Let G be a content-free grammar. Suppose that P capital contains a production of the form A into x1, B capital x2. Assume that A capital and B capital are different variable and that B maps to y1 or y2 or so on, or yn is a set of all production in the set P capital that have have B as a left side, and let G capital with head, it consists of V capital, T capital, C S capital and P with head, P a grammar in which P capital with head is constructed by letting such production A capital into X1, B capital X2 from P and adding to it A maps to X1, Y1, X2, or X1, Y2, X2, so on, or X1, Y, and X2. Then the language generated by the grammar G capital with head coincide with the language generated by the grammar G capital. The proof. Suppose that the word belongs to the language generated by the grammar G capital, so that S maps the star with this grammar into word WB. The subscript of the derivation thing implies is used here to distinguish between derivation with different grammars. In this derivation, does not involve the production one, yeah, where A capital into X1, B capital X2. Then obviously, as implies with star by grammar G capital with head into the word W. If it is thus, then look at the derivation of the first time this formula, yeah, is used. Then B so introduced eventually has to be replaced. We lose nothing by assuming that this is down immediately. Thus, as implies star G into U1, A capital U2 implies by G U1, X1, B capital X2, Y U2 implied by G U1, X1, Y G J X2, U2. But with the grammar G capital with head, we can get S implies with star by grammars G capital with head to U1, A2, U2 implied by the grammars G capital with head U1, X1, UG, X2, U2. Thus, we can reach the same syntactical form with G capital and G capital with head. If the formula 1 is used again later, we can repeat the argument. It follows them by induction on the number of times the production is applied, that as imply star by grammar G capital with head word W. Therefore, if the word W belongs to the language is generated by the grammar G capital, then this word belongs to the language generated by the grammar G capital with head. By similar reasoning, we can show that if the converse statement that if W belongs to the language generated by the grammar G capital with head, then W belongs to the language which is generated by the grammar G, yeah, which completes the proof, yeah. Theorem 6.1 is a simple and quite intuitive substitution rule. The production A into x1, b capital x2 can be eliminated from a grammar if we put in the place the set of production in which b is capital is replaced by all words it derived on one step. In this result, it is necessary that a capital and b capital be different variable. Example, consider grammar, Boolean grammar, yeah, with production a into a or a capital or a b capital c, and b into a b a capital or b. Using this suggestion substitution for the variable b capital B gets the grammar G capital with head with production a into a or a capital or a b c or a b c, b into a capital or b. The new grammar G with head, G capital with head equivalent to the grammar G capital. The string B, C has the derivation A implies a capital implies B capital C implies B C in the grammar G capital, and the corresponding derivation A imply as a capital implies B C in the grammar G capital with head. Notice that in this case, the variable b capital and its associated production are still in the grammar, even so they can no longer play a part in any derivation. We shall next show how such unnecessary production can be removed from a grammar, removing endless productions. One invariably want to remove production from the grammar that can never take part in any iteration. For example, in the grammar whose entire production set is S into A S capital B or empty word lambda or A capital A into A capital, the production S capital into A really play no role, as a capital cannot be transformed into terminal string, while a capital can occur in a word derived from S capital. This can never lead to a sentence. Removing this production leaves the language unaffected and is a simplification by any definition. Let G capital, which consists BTCP, be a context-free grammar. A variable A from V capital is said to be useful if and only if there exists at least one word in the language which generated grammar G, such that S implies with star into X, A capital Y implies star into word W with XY from the set V union with T capital star. In the word, a variable is useful if and only if it occurs in the last one derivation. A variable that is not useful is called useless. A production is useless if it involves any useless variable. Example. A variable may be useless because there is no way of getting a terminal word from it. The case just mentioned of this kind. Another reason a variable may be useless is shown in the next grammar. In a grammar with the star symbol C capital and production C into S capital into A capital into a capital or the empty word lambda, b into b a capital, the variable b capital is useless, and so is a production b capital into b a capital. Also, B capital can derive a terminal word. There is no way to can achieve as capital implies star x B capital Y. This example illustrates the two reasons why a variable is useless. As because it cannot be reached from the star symbol, or because it cannot derive a terminal word. A procedure for removing atlas variable and production is based on recognizing these two situations. Before we present the general case and the corresponding theorem, let us look at another example. Example 6.3. Eliminate useless symbols and production from the grammar G, where V consists of the set of variable consists of S capital, A capital, B capital, C capital, and the terminal is the terminal alphabet is A and B, with P consisting of is a set of production which consists of S into A, S capital, or A capital, or C, and A capital into A, B capital into AA, S C capital into A C capital B. First, we identify the set of variables that can be lead to a terminal word. Since A capital into A and B capital into AA, the variable A capital and B belongs to this set. So does C capital because so does S capital because S capital imply A capital imply A. However, this argument cannot be made for C capital, thus identifying it is as astless. Removing C capital and its corresponding production, we are led to the grammar G capital 1 with variable V capital 1 is consists of S capital A capital and B capital terminals. T capital which consists of letter A, and production S into A, S capital or A capital, A into A, B capital into AA. Next, we want to eliminate the variables that cannot be reached from the start variable. For this, we can draw a dependency graph for the variables. Dependency graph are a way of realizing dependency graph are a way of visualizing complex relationship and are found in many applications. For context-free grammars, a dependency graph has its vertices labeled with variable. With an edge between vertices C capital and D capital, if and only if there exists a production of the form C into C capital into X, D capital Y. A dependency graph for the set of variable V capital 1 is shown in the following figure. A variable is used only if there exists a path from the vertex labeled S capital to the vertex labeled with variable. In our case, the figure shows that B capital is useless. Removing it and the affected production and terminals, we are led to the final answer. The grammar G capital hat is equal V capital with cat, T capital with cat, S capital, P capital with cat with um, V capital with cat consists of the variable S capital and A capital. T is terminal, the set of terminals. T capital with cat consists of the letter A, and production S into A, S capital or A capital, and A capital into A. The transformation of this process leads to a general construction and the corresponding theorem. Theorem 6.2. Let G be a context-free grammar, then there exists an equivalent grammar G capital with hat that does not contain any useless variable or production. Proof. The grammar G capital with hat can be generated from the grammar G capital by an algorithm consisting of two parts. In the first part, we construct an intermediate grammar G1 such that the set of variable V capital 1 contains only variable A capital for which A capital implies star to the word W, which is belongs to T's star. It's possible. The steps in the algorithm are set the V capital 1 to the empty set. The second, repeat the following step until no more variables are added to the set V capital 1. For every variable A capital from V for which the set P capital has a production of the form A into x1, x2, where and so on, xn, xn with all xi belongs to V capital 1 the union T at A capital to V capital 1. Take the set P1, P capital 1 as all production in P capital whose symbols are all in the set V1 union T. Yeah? Where this procedure terminates, it is quality clear that if A capital belongs to the set of variable V capital 1, then A capital implies star the word W from T capital star is possible in derivation with G1. The remaining area is whether every A capital for which A capital implies star W, which is equal AB, and so on, is added to the set V capital 1 before the procedure terminates. To see this, consider any such variable A capital and look at the partial derivation tree corresponding to that derivation. See on this figure. Yeah. At level K, there are only terminals, so a variable A capital I in the level K minus 1 will be added to the set V capital 1 on the first pass through step 2 of the algorithm. Yeah. Any variable as level K minus 2 will then be added to the set V capital 1 on the second pass through step 2. The set time through step 2, all variables at level K minus 3 will be added. and so on. The algorithm cannot terminate while there are variables in the tree that are not yet in the set V capital 1. Hence, a capital will eventually be added to the set V capital 1. In the second part of the construction, we get the final answer the grammar G capital head from the grammar G capital 1. We draw the variable dependency graph for the grammar G capital 1, and from it find all variables that cannot be reached from as capital. These are removed from the variable set as are the production involving them. We can also eliminate any terminal that does not occur in some useful production. The result is grammar G capital with head such form, yeah. Because of the construction, the grammar G capital with head does not contain any useless symbol or production. Also, for each word from the language generated by the grammar G capital, we have a derivation S capital implies star X A capital Y implies star the word W. In the construction of the grammar G capital with head retrieves A capital and all associated production, we have everything to need to make the derivation as capital star as capital implies star with grammar G capital with head X A capital Y implies star with grammar and G capital head onto the word W. The grammar G capital head is constructed from the grammar G capital by the removal of productions, so that the set P capital head is subset of the set P capital. Consequently, the language generated by the grammar G capital with head is a subset of the language which is generated by the grammar G capital. Putting the two results together, we see that the grammar G capital and the grammar G capital with head are equivalent. This completes the proof of the theorem. Removing lambda production. One kind of the production that is sometimes under the variable is one in which the right side is the empty word. Definition. Any production of the context-free grammar of the form A capital into the empty word lambda is called a lambda production. Any variable A capital for which the derivation A capital implies star the empty word lambda is possible is called nullable. Grammar maybe generate a language not containing the empty word lambda, yet have some lambda production on a label variable. In such case, lambda production can be removed. Example, consider the grammar as capital into A S1B, S1 into A S capital 1B or lambda or empty word lambda with a start variable S. This grammar generates the lambda free language which consists of such words A in power n, B in power n, where n belongs to the set of positive integers. The lambda production is capital 1 into empty word lambda can be removed after adding new production obtained by substituting the empty word lambda for S capital 1 where it's occurring on the left, on the right. Doing this, we get the grammar S capital into A, S capital 1, B, or AB. So, sorry, here misprint must be. And S1 into A, S1B, or AB. We can easily show that this new grammar generated the same language as the original one. In more general situations, substitution for lambda production can be made in a similar, although more complicated manner. Theorem. Let G capital be any context-free grammar with empty word lambda not in the language generated by this grammar. Then there exists an equivalent grammar G capital with hat having no lambda production. Proof. First, we find the set V capital N of all new label variable of the grammar G capital using the following steps. That's the first step. For all production, A capital into empty word lambda, put A capital into V capital N. Repeat the following step until the further variable are added to the set V capital N. For all the production, B capital into A1, A2, so on, AN, where A1, A2, and so on, AN are in the set V capital N, put B into the set V capital N. Once of the set V capital N has been found, we are ready to construct set P capital with hat. To do so, we look at all production is a set P capital of the form A into X1, X2, so on, Xm, where M is any positive integer, where each Xy belongs to the set V capital union T capital. For this such production of the set P capital, we put into P capital with hat that production as well as all those generated by replacing the label variable with lambda in all possible combination. For example, if xi and xj are both labeled, there will be one production in the set P capital hat with xy replaced with empty word lambda. The one in which xj is replaced with empty word lambda, and the one in which both xy and xj are replaced with the empty word lambda. This is one exception. If all xy are labeled, then the production A into empty word lambda is not put into the set P capital hat. The argument that this grammar G capital hat is equivalent to the grammar G capital is straightforward and we be left to the reader. So we complete the proof of this theorem. So next example, example 6.5. Find the context-free grammar without lambda production equivalent to the grammar defined by S into A capital, B capital, A, C capital, A into B capital, C capital, B capital into B or empty word lambda, C capital into D capital or empty word lambda, D capital into D. From the first step of the construction in the theorem 3.3, we find that the label variables are A capital, B capital, and C capital. Then following the second step of the construction, we get S into A capital, B capital, A, C capital, or B capital, A, C capital, or A capital, A, C capital, or A capital, B capital, A, or A, C capital, or A capital, A, or B capital A, or A A into B capital, C capital, B capital into B or empty wall lambda, the C capital into D capital or empty wall lambda, D capital into D, removing unit production. As we have seen in theorem 5.2, production in which both sides are single variable are at time undesirable. Definition. Any production of a context-free grammar of the form A capital into B capital, where A, B belongs to B capital, is called a unit production. To remove unit production, we use the substitution rule discussion in theorem C6.1. As the construction in the next theorem show, this can be done if we proceed with this sum car. Theorem 6.4. Let G capital be any context-free grammar without lambda production. Then there exists a context-free grammar G capital with head of such form that does not have any unit production, and that is equivalent to the grammar G capital. The proof. Obviously, any unit production of the form A capital into A capital can be removed from the grammar without effect, and we need only consider the production of the form A capital into B capital, where A capital and B capital are different variables. At first it may seem that we can use theorem 6.1 directly with the word x1 is equal to the word x2 is equal empty wall lambda to replace A capital into B with A capital into y1 or y2, so on, y or yn. But this will not always work. In the special case, A capital into B, B capital into A, the unit production are not removed. To get around this, the first find for each A capital all variables B capital so that A capital implies star B. Yeah, we can do this drawing the penciling graph with the edge C capital D capital O. Whenever the grammar has a unit production C capital into D capital, then the formula form holds whenever there exists a wall between A capital and B capital. The new grammar G capital hat is generated by first putting into P hat all non-unit production of the set P capital. Next, for all variable A capital and B capital substituting the formula for, yeah, we add to the set P capital hat by the following way: A into y1 or y2 or so on, or yn, where B capital into y1 or y2 or so on or yn is a set of all rules in the set B capital star with B capital on the left. Now that B in capital this production, yeah, B capital to y1 or y2 so on or yn is taken from the set B capital hat, and none of the yi's can be single variable, so that no unit production are created by the last step. To show that the resulting grammar is equivalent to original one, we can follow the same line of reasoning as in theorem 6.1. So good, we finish this the proof of this theorem. Next example, example 6.6. Remove all unit production from S capital into A capital A or B capital into A capital or BB, A capital into A or BC or B capital. The dependency graph of the unit production is given as the following figure. Yeah? S into B and A. We see that that S capital implies star A, S capital implies star B, and B capital implies star A, and A capital implies star B capital. Hence, we add to the original non-unit production S capital into A capital A, A capital into A or BC, B capital into BB. The new rules, S capital into A or BC or BB, A capital into BB, B capital into A or BC, to obtain the equivalent grammar, S capital into A or BC or BB or A capital A capital into A or BB or BC, B capital into A, BB, BC. Note that the removal of the unit production has made B capital and the associated production useless. We can put all these results together to show that grammars for consent-free languages can be made free of useless production, lambda production, and unit production. Theorem. Let L capital be a consent-free language that does not contain the empty word lambda capital. Sorry, empty word lambda. Then there exists a consent-free grammar that generates language L capital and that does not have any unless production, lambda production, or unit production. The proof. The procedure given in theorems 6.2, 6.3, and 6.4 removes these kinds of production in turn. The only point that needs reconsideration is that the removal of one type of production may introduce production of another type. For example, the procedure removing lambda production can be creating new unit production. Also, theorems 6.4 require that the grammar have no lambda production, but note that the removal of unit production does not create a lambda production, and the removal of the useless production does not create a lambda production or a unit production. Therefore, we can remove all undesirable production using the following sequence of steps. The first, remove lambda production. The second, remove unit production. The third, remove useless production. The result will then have known as this production, and the theorem is proved. So I finish my lecture. Thank you for your attention. Please send me a message that you listen to my lecture. I wish you good luck, good health, and the Finnish, Russian, Ukrainian war. Goodbye.